Hello, welcome to the channel, or welcome back. I'd like to show off this radio that I'm working on now. It's a Norelco B5X98A, made in 1959 in Holland. I'm about 85% finished with the restoration. But indeed, this radio does not have an output transformer. So what I'd like to do today is we'll take a look at the chassis, and then we'll go through why almost all of these radios back in the 50s had output transformers and why they needed them. When I'm finished with the restoration, we can go back, hopefully in a part 2, go over the particulars of the restoration. But more importantly, discuss how Philips got rid of their output transformer in this radio, and the changes that they had to make in order to do that. So thanks for watching, and we'll take a look at the chassis now. Okay, now I'll look at the chassis. The chassis is in my my holder. I must say it hangs, but certainly during the restoration it enables you to keep the radio safe and to get to every part of the radio. Where is the output transformer? There isn't any. There's the FM section, there's my antenna. Usually you would see an output transformer about in the middle here, but there isn't any. It has an EZ80 as a rectifier. It has a really a fairly big main transformer, and you can adjust it for, I think, about 4 or 5 different voltages. It's set to 110 now. It goes to 110, 125, I think 220 and 240. But indeed, there is no output transformer. Let's take a look at the underside. Okay. We're looking for a hidden output transformer, and of course there isn't one. So there we go. Hopefully we'll get this restoration finished, and we'll go over the particulars of the restoration. All right. So here is a Nordmendy and a Telefunken. You can see the output transformer on both of them. So then what does an output transformer do, and why is it necessary? Well, first of all, it blocks the DC voltage coming off the plate of the power tube. Next, it matches the impedance. So the impedance of a vacuum tube is about 5,000 ohms, and the impedance of a speaker is about 4 to 8 ohms. You need to match the impedance to get the most power transfer. Next, it adjusts the voltage and the current. And lastly, it protects the speaker terminals, which would ordinarily get high voltage from the power tube, but they get low voltage. Okay, so bear with me a little bit here. I don't have an electronics background, so when it comes to impedance matching, without using formulas, it's a little difficult for me to understand. So I like to think of it like this. So what you're seeing here is a vacuum tube. It has high impedance, and it has a high voltage, but a low current. So picture this muscular guy. He's got lots of voltage, lots of power, and he works best when he's pushing against a really thick spring.
In fact, the spring doesn't move that much. There's a not, and the distance that the spring moves is equivalent to the current. So this is a vacuum tube. It's high impedance, high voltage, and low current. Now let's take a look at a speaker. A speaker has low impedance. It has usually about 8 ohms of impedance. And impedance is equivalent to resistance with the added alternating current component. It doesn't have a lot of voltage. A speaker doesn't like voltage, so it doesn't have a lot of power. But what it does have is significant current. So here's my depiction of a speaker. You've got some guy with very little muscles, so he doesn't have a lot of power, not a lot of voltage. But he's got long arms, and those long arms can move the spring a lot. So you can see that there's a big difference between the vacuum tube and a typical 8 ohm speaker. Okay, now what's going to happen if you attach the vacuum tube directly to the speaker? Well, the vacuum tube has lots of voltage. It's really strong. And it's going to go up against the speaker, which has a low impedance, and it's going to try to push like as if the speaker has high impedance. So it's going to push against this skinny spring as if it's pushing against the thick spring. Well, the first thing that's going to happen is the tube's going to fall on its face because it pushed too hard. And the second thing that's going to happen is the speaker's going to break. You can see the springs there are broken because he pushed so hard. So you are thus unable to connect the high impedance vacuum tube to the low impedance speaker. And if you do, you're going to blow your vacuum tube, because once it falls, it's going to suck up more current and heat up and burn up. And you're also going to probably burn out the coil on the speaker. Okay, let's take a look at some real numbers. So on the left is the vacuum tube. You can see there's an EL84. This is a typical amplification tube for most German radios. And the voltage coming out of the plate is 250 volts DC. Now the AC voltage is your signal, and that is 100 volts peak to peak, going from 200 volts to 300. The impedance of the tube is 5,000 ohms, and the current is 20 milliamps. Okay, it goes into the output transformer, and there's a 25-to-1 coil ratio. This is for a typical 1959, 1960 tube radio. And the speaker now is 8 ohms. It has no DC voltage. Its signal, the AC part of it, is 4 volts peak to peak. That's your signal. And the current is 500 milliamps. So you can see the output transformer has achieved its goals. And again, this is what you've achieved. You've blocked the DC voltage. You've matched the impedance, so there's very good power transfer. You've adjusted the voltage and the current. And because you've gotten rid of the DC voltage, the speaker terminals are now not hot and can be worked on, even if there is an output, an input on the radio for another speaker. So I'm hoping to finish up the restoration, and when I do, we'll present the whole restoration and how Philips managed to get rid of the output transformer. Here is the schematic of the output section. As you can see, there are two output tubes in a very interesting combination. Thanks for watching. Have a great day.